So this lecture is about implicit polymorphism. Implicit polymorphism. So in the previous lectures, we learned 3 different type systems with polymorphic types. On the right extreme, we have system F. On the left extreme, we have predicative polymorphic lambda calculus. And in between these 2 polymorphic type systems, we have lead polymorphism. Lead polymorphism is basically predicative polymorphic lambda calculus with this lead binding. And we learned that this lead polymorphism offers the best of both worlds. From predicative polymorphic lambda calculus, it inherits this decidability of type reconstruction, decidability. And from system F, we partially inherit the rich expressivity. So the expressive power is almost as good as system F. So lead polymorphism offers the decidability and sufficiently powerful, sufficiently expressive type system. So lead polymorphism is a good basis for practical programming language. And the plan now is we'd like to develop further this lead polymorphism to formulate a practical programming language with powerful type system. And in the case of this lead polymorphism, we say that its polymorphic type system is explicit, in that we annotate the variables with the types. So in other words, the type system is explicit because the polymorphic types are explicitly specified in expressions. So for example, in order to create polymorphic identity function in lead polymorphism, you have to explicitly declare type variable alpha with this type abstraction, and then you'd declare variable x with type. So here we explicitly annotated the variable x with type alpha, and then the body is x. So this is the way that you declare, this is the way that you create polymorphic identity function in lead polymorphism, where everything is explicit. You explicitly declare type variable, you explicitly annotate variable x with its type alpha. So in this way, we explicitly create this expression with the polymorphic type, all alpha, alpha, arrow alpha. So this lead polymorphism is explicit, but for the foundation of practical programming languages, we'd like to adopt this implicit style. We'd like to use this implicit polymorphism. Implicit polymorphism. Where the key idea is, we don't want to explicitly declare type variable like this one, or we don't want to explicitly annotate this variable with its type. Instead, we for this polymorphic identity function, we don't use this type abstraction and type annotation. So in the case of implicit polymorphism, we only have this lambda x dot x. Notice that there is no type variable, no type abstraction here, and there's no type annotation. And because of this lack of explicit type declaration and explicit type annotation, we obtain polymorphic type. So for instance, later we will see that this lambda x dot x can be assigned this polymorphic type for alpha, alpha arrow alpha. So to summarize the story so far, we identified lab polymorphism as a compromise between predicative polymorphic lambda calculus and system F. This lab polymorphism offers decidability in type reconstruction and also offers sufficiently expressive type system. And this lab polymorphism is explicit in that you have to explicitly declare this type variable, and you have to also explicitly annotate this variable with its type. So these polymorphic types are explicitly specified. But that's not a good basis for practical programming languages because we don't want to declare type variable in this way. So as foundation for more realistic, more practical programming languages, we'd like to use this implicit polymorphism, where everything is implicit. These polymorphic types are implicitly given, and the type for this lambda abstraction is also implicitly given. So we'd like to use this implicit polymorphism as the foundation for practical, realistic programming languages with type systems. So here's an example. So let's consider this one, lambda x dot x, in implicit polymorphism. Notice that it is implicit because we don't annotate x with some concrete type like a bool. So we don't do this here. So it is really implicit. And in implicit polymorphism, we can assign some concrete type to this lambda abstraction. So for instance, bool arrow bool is legitimate type that can be assigned to this identity function because this lambda abstraction can definitely serve as the identity function for Boolean. But at the same time, it is also fine to assign int to arrow int to this lambda abstraction because the same lambda abstraction can serve as the identity function for integers as well. Then we can assign another type, for instance, integer arrow, integer arrow, integer arrow, integer, and so on. All these types are valid candidates for types that can be assigned to this lambda abstraction. So all these are fine. But we think about the type of this lambda abstraction in the context of polymorphism. Perhaps we'd like to assign the most general type, namely for alpha, alpha arrow alpha, somehow. So in other words, we wish this lambda abstraction can be assigned this polymorphic type because in some sense, all these particular instances, all these particular monotypes are subsumed by this polymorphic type in the sense that you can always instantiate this polymorphic type to one of these monotypes. So in this regard, we can say that this polymorphic type is the most general type that can be assigned to this lambda abstraction. Is the most general type. So we say that this type, the most general type that can be assigned to this lambda abstraction, we call such a type as principal type. Principal type for this lambda abstraction. So working definition for this principal type is the most general type that you can assign to given expression. So later, when we study the type reconstruction algorithm, we will actually develop an algorithm that calculates the principal type for given expression. So this is the example of typing in implicit polymorphism. In implicit polymorphism, there is no type annotation here. there's no type annotation, and there's no explicit type variable declaration either. We don't use this capital lambda alpha. Still, we will be able to assign this principal type, the most general polymorphic type, to this expression. That's actually the direction of developing implicit polymorphism. So remember that all these concrete monotypes are valid types for this lambda abstraction, but in some sense they are not the most general one. The most general one is this polymorphic type, and this polymorphic type is called principal type. Now let's develop the syntax and the type system for this implicit polymorphism. So implicit polymorphism. So implicit polymorphism is almost the same as lab polymorphism, but without type annotation and type abstraction and type application. So we just remove all the type related stuff from lab polymorphism, and then we obtain this implicit polymorphism. So types are still stratified into two layers. So we have monotype A, arrow A, alpha, and we also have polytype U, for alpha U, A. So this is no different from lab polymorphism. And expressions are clearly different. So first of all, we have this lambda abstraction, but unlike in lab polymorphism, we don't have this type annotation. In lab polymorphism, we have this type annotation. But remember, we no longer use a type annotation in implicit polymorphism because everything is implicit. So we don't specify the type, and we have application. And we also have lab polymorphism. And again, we don't have this type type annotation. In the case of lab polymorphism, we annotated this variable x with some polytype, but everything is implicit now, so it is not explicitly specified. So this type annotation is gone. So the syntax for lab binding is very simple. Just like in OCaml programming, there's no type annotation here. And moreover, there's no type abstraction. This is implicit, so we don't have this one. And because we don't have a type abstraction, we don't have a type application either. So it makes no sense to have this one only without this type abstraction. So these two guys are also gone. So this is the entire syntax for expressions. And typing context, values are just lambda abstraction. And typing context, gamma, is either empty or variable x with polytype, because this variable from let binding can have polymorphic type. And we have type variable declaration. This is typing context. Now, what is the judgment for typing rules? So in lab polymorphism, we use this typing judgment, gamma turnstile expression E has type U, which says that under typing context, the gamma expression E has a type U. Now we use a slightly different typing judgment, which is gamma right triangle expression E has type U. And this thing means that this new form of a typing judgment means under typing context gamma, expression E is typable with the polytype U. Notice that it is typable, which suggests that it is just one potential type that can be assigned to expression E. So for instance, as we will see later, lambda x dot x can be assigned, is a typable with, this expression is typable with, for instance, bool arrow bool, which is a legitimate type, or int arrow int, or this is a polymorphic type, alpha arrow alpha. So there are many different candidates that can be assigned to this expression. So that's the reason why we say expression E is typable with some polytype U, which suggests that this polytype U is just one of the candidates that can be assigned to expression E. Of course, later we will try to find the most general type, but the interpretation of this judgment, this typing judgment is expression E is typable with the polytype U. And formally, what this judgment means is this one. So formally, what this means is that there exists an expression E prime in left polymorphism. So notice that expression E is from implicit polymorphism, and expression E prime is from left polymorphism. And the relation between the two expressions is, first, the expression E prime must have type U. And the type for this expression E prime is unique if it is typable at all. In other words, if we can assign a valid type to expression E prime, it must be unique and it must be U. And secondly, if we erase every type-related annotation or declaration from expression E prime, we get that expression E. So we actually learned the definition of erase, this eraser function, in the earlier lecture. But the idea is simple. Just erase, literally erase or remove every type-related stuff, type-related annotation or declaration or application in the expression E prime, then you get the expression E. So that's the interpretation of this judgment for implicit polymorphism. So this is judgment that we use for implicit polymorphism, and this one is from left polymorphism. And it's straightforward actually to define this erasure function as a recursive function. For instance, erase of lambda x dot a dot e would be just to erase this type annotation. So it would be lambda x dot erase E. And what about type abstraction? Erase capital lambda alpha dot E. So the idea is just get rid of this type-related stuff. So we obtain erase of E. And similarly, the type application is also ignored. So this is type-related stuff, so we erase it. We obtain erase of E. And what about let binding? Let x u e e prime. So this is also easy. Just to get rid of this type-related stuff, and then we get back let x erase e in erase e prime. So it's just a simple recursive function that propagates the application to every part of the given expression to get rid of type-related stuff, like this one, or this one, or this one, or this one. So this is the definition, the meaning of this typing judgment. Expression E is typable with polytype U, perhaps among many different candidates. So for instance, lambda x dot x is typable with, of course, bool arrow bool. It is also typeable with int, arrow int, and so on. And in particular, it is typeable with a polymorphic type for alpha, alpha, arrow alpha. So notice that many different types can be assigned to the same expression. So there are just many candidates. In contrast, in the case of a lab polymorphism, if this expression is typeable at all, it must be given a unique type. So this is fixed. So this is the syntax for implicit polymorphism, which is basically let polymorphism without type annotation and type abstraction application. So there is no type related stuff in implicit polymorphism, as indicated by the syntax here. And we use this typing judgment, which says expression E is typeable with polytype U among many candidates, perhaps. Now, it's time to develop typing rules for this typing judgment. So let's develop the type system for implicit polymorphism. Remember that expressions are variables, lambda abstractions, application, and lab polymorphism. And there is no type annotation here. Let's develop the typing rule. First, the variables. We'd like to type variable x. For variable x, corresponding type binding must be found in typing context gamma, in which case we assign type U. And what about this lambda abstraction? So unlike lab polymorphism, which annotates this variable x, in the case of lab polymorphism, the syntax looks like this one. So this variable x is explicitly annotated with monotype A, but that's no longer the case in implicit polymorphism. This variable x is not annotated with monotype at all. So we have to make a guess. Of course, we will not make a guess. We will not make a random guess later. The type reconstruction algorithm will find the best type for you. But at the moment, let's just assume that we make a good guess on the type of a variable x. So if we assign type A to this variable x, and if expression E produces type B, that is, expression E is typeable with a valid type B, with the assumption that x is type A, then everything is good. So in which case, we can assign A arrow B to this expression. So this is for, this is arrow introduction rule. So notice that here we make a guess. The type of a variable x is not fixed in advance. It will be decided at the time of type checking. And it's because of this rule, this arrow introduction rule, that we can assign, for example, int arrow int to this expression, or bool arrow bool to the same expression, because we can make a different guess. In this case, we guess x is a type int, and in this case, we guess that variable x is a type bool, and so on. So that's the first major difference from lab polymorphism, where you are free to assign any type to variable x as far as the expression E is given a valid type. You are not permitted to use any type. So for instance, if you assign a bool to variable x, in which case, let's just say expression E cannot be given a valid type, then this guess is wrong. So you have to make sure that expression E here, the body of this lambda abstraction, must be assigned a valid type. And the type of this lambda application is easy. So if expression E has a type A arrow B, and expression E prime is type A, then this application has a type B. this arrow elimination rule. What about let expression, let binding? Let x expression E in expression E prime. So first, we find the type for this expression E, and in general, it can have a polymorphic type. And then we introduce this type binding, X is type U comes from here, and then we type check the expression E prime. If expression E prime is type A, then the entire let binding has type A. This is the typing rule for let binding. And with these rules, there's no way to introduce polymorphic types. So in the case of let polymorphism, the type system for let polymorphism has all these rules, like a variable rule, this variable rule, and for arrow introduction rule, and arrow elimination rule, and also let rule. And for all introduction rule, for all elimination rule. But in this implicit polymorphism, we don't have those rules that correspond to this for introduction rule and for all elimination rule. And it makes sense because we don't have this type application, type abstraction, and type application. In other words, if we had this type abstraction and type application, we would have for introduction rule and for all elimination rule. But unfortunately, we don't have this type abstraction and type application. So there should be some different mechanism that allows us to use polymorphic types. So it turns out that in implicit polymorphism, we have two typing rules with different names that correspond to for introduction rule and for elimination rule. And they are generalization rule and specialization rule. So here gen stands for generalization, and here spec stands for specialization. And this generalization rule goes, I would like to type this expression E, and I believe that we can assign polymorphic type with the type variable alpha. So we are free to introduce fresh type variable alpha here. Notice that alpha is really fresh, that has not been generated before. And then if expression E has a type U, and inside this type U, of course, you may use type alpha. Then we can generalize. If we move top to bottom, then we generalize this type U and introduce for alpha.u. So it almost looks like this for introduction rule, but it's not for introduction rule because we are not delivering it type abstraction here, such like this. Everything is implicit, so it's your responsibility to introduce type variable, this fresh type variable alpha. You have to find a type variable and you have to introduce yourself. So this is the generalization rule, which corresponds to this for introduction rule. And corresponding to this for elimination rule is the specialization rule. And specialization rule is, suppose that you have an expression of polymorphic type. Expression E has this polymorphic type. Now, you'd like to specialize this type variable. So assuming that A is a valid monotype, this expression E can be assigned this type, A for alpha in U. So now you specialize this type variable alpha to monotype A. In this way, you specialize. So specialization rule corresponds to for elimination rule, and this generalization rule corresponds to this for introduction rule. And also remember that we don't have this for introduction rule for elimination rule because we simply don't have this type abstraction and type application. We don't have these two constructs in this language. So everything is implicit. So it's your responsibility to find this type variable alpha. It's your responsibility. And it's also your responsibility to find a suitable monotype. In the case of lab polymorphism, this type variable alpha is explicitly given by the programmer, and this monotype is also given explicitly by the programmer. But now everything is implicit, so you are responsible for finding such a type variable alpha, and you are responsible for finding such a monotype A. So this is the type system for implicit polymorphism. So let's see an example of typing an expression. So we'd like to use the example that should be already familiar now. So which is, our goal is to type check this expression lab f lambda x dot x in f0 f true. So notice that we introduce a polymorphic identity function, and we apply this polymorphic identity function really polymorphically in two separate contexts. In the first context, we use this polymorphic identity function, for integers. And in the second context, we use the same identity function for Boolean. So we truly reuse this polymorphic function polymorphically for integer type and Boolean type. So if everything goes okay, then perhaps we'll be able to assign type int times bool, assuming that product types are already available. So let's use this one. So first, we have to show that this lambda abstraction is typable with polymorphic identity type, polymorphic type. So let's see how. So the goal is, we'd like to show this lambda abstraction indeed has polymorphic identity function, the type of polymorphic identity function, so namely for alpha, alpha, arrow, alpha. Yes, of course you can assign int to arrow int. So this is easy to construct. For example, in this case, your guess is int. Your guess is this variable x must be assigned the type int. So your guess is this one. Then the body x has a type int. And as a result, the whole lambda abstraction has a type int, arrow int. So this is okay, but later on, you will realize that your guess here was actually really bad choice, because with this typing, this f applied to 0 is typable, but this f applied to true is not typable, because you cannot actually apply function of type int to arrow int to Boolean constants. So it's okay to assign this int arrow int to this identity function as far as typing is concerned, but for the type checking the entire expression, this is actually better choice. So to minimize the chance of failing to type check the given expression, you'd like to assign the most general type or principal type to this lambda abstraction. And this is where we use this generalization rule. So you have to make a good guess. You have to make an educated guess. And perhaps you want to introduce type variable here. So you are ready to assign this polymorphic type. Now you'd like to type check this lambda abstraction. Now your guess is this variable x must be given this type variable alpha, in which case the body has a type alpha, so the entire lambda abstraction has type alpha, arrow alpha. Now you apply this generalization rule and assign this for alpha, alpha, arrow alpha to this lambda abstraction. So that's how we assign polymorphic type to given expression. So notice that in order to introduce this polymorphic type, you have to use a generalization rule, just like you have to use for all introduction rule in lab polymorphism. So that's the first part in the type reconstruction. Now, let's try to type check this one. Well, the second component of this pair is completely analogous, so let's just focus on the first component. So now, we'd like it to type check f applied to 0 in this context where f has this variable f has this polymorphic type. So f has type this for alpha, alpha, or alpha. And our goal is to assign integer, because if this expression is typeable at all, then it must be assigned integer type. Because this is an identity function and this is an integer, so the result of applying f to 0 is going to be also integer. So our goal is to somehow assign integer type to this expression f applied to 0, where f has a type, this is polymorphic type. Notice that f does not have int arrow int yet. It is just a polymorphic type. So perhaps our instinct said somewhere in this typing derivation you have to use specialization rule and specialize this polymorphic type to concrete type int arrow int. So let's do this. So perhaps you have to show that this f has type int arrow int, and then the argument 0 has a type int. As a result, this f applied to 0 has a type int. So f has type int arrow int, 0 has a type int. So f applied to 0 has a type int. Then the question is, how do we specialize the type of this variable f from this polymorphic type to this concrete monotype? And that's where we use specialization rule. So under this typing context, f has this polymorphic type. So this is basically the application of a for rule. Now let's apply the specialization rule. So if we go back to specialization rule, you have an expression of polymorphic type, and it's your responsibility to make a good guess on the monotype A that will be substituted for this type variable alpha. So you choose a suitable monotype A here and substitute it for type variable alpha. It's your guess. So let's try to make a guess here. So our guess here is alpha should be instantiated to integer type int. Then, thanks to this specialization rule, we can convert the type of this f from this polymorphic type to int arrow int. So that's how we use this specialization rule. And in the end, we can assign type int successfully assign type int to this f applied to 0. Likewise, in type checking f applied to true, we will see another instance of specialization rule. So here, f also has this polymorphic type, and perhaps we will specialize it to bool arrow bool. So during the type checking of this expression, we will specialize this polymorphic type to int. And during the type checking of this expression, we will specialize the same type to Boolean. So we really reuse the same function f polymorphically. First for integer, second for Boolean. So this example illustrates how we can define polymorphic functions in this language. Here we introduce a polymorphic identity function and use this polymorphic identity function really polymorphically into different contexts for integers, for booleans. So this is the prototypical pattern of introducing polymorphic expressions and also using the polymorphic expressions in different contexts really polymorphically.